So good morning, welcome to the class. So this is discrete maths, and then I'm Wing Kai Hon. So yeah, I'm very nervous today. It's because I've not been teaching for a whole summer, so I nearly forget how to teach. So forgive my nervousness. Okay, so here for this course, so let me give you some basic information. So we have some lecture notes that you may download it from my course webpage. So it is easy to get as long as you remember my name. So my name is Wing Kai Hon, and then you can write me emails, and then you can just call me Kai. So dear Kai, then that's okay. No need to write dear teacher or whatever. Dear Kai, that's okay, and that's what I want. And then So if you want to access my own web page, it is easy. You go to the department web page here, www.cs.nthu.edu, and then you press the slash, and then there's a tilde, WKHON. This is my web page, and this is also my email account. So if you want to write me email, then it is easy. So my email address is wkhon@cs.nthu.edu.tw. Is that okay? Good. Okay. So far, we have 2 excellent TAs, but we may be adding one more later, maybe, I don't know. So we will have some announcement of the course, like when we will have the exams, when we will have a tutorial, and then anything special, maybe I'm getting sick or whatever, okay, through this system. So we will sending you messages through this ILMS system, okay? Now, let me tell you what is this course about. So the title of this course is very strange. It is called Discrete Mathematics or Discrete Math. So the focus here is something that is discrete. So first of all, what is the opposite of discrete? Anyone? What is the opposite of? So discrete and what? If something that is not discrete, yes? Combination is also a kind of discrete things. You will see. So let me tell you, discrete things are something that we can count it one by one. So you can see it. Like you read a book, and there are many sentences. So the number of sentences in a book is something that we can count one by one. So a book is something that is discrete. It consists of 1, 2, 3, a countable number of sentences. Also, within each sentence, it has some words that we can count. So anything that we can count should be count one by one is considered discrete. Okay, so this can be extended to some very strange things, like when we write a mathematical proof. You want to prove something. So the proof itself is some finite number of arguments. So it is a discrete thing. So we will talk about this inside this course. Of course, so he has just introduced the word combinations. So combinations is also discrete. It is in the sense that we are counting how many ways we can do things, right? So this is how many ways that we can go to the McDonald's and then have a different meal every day, so that we have a different kinds of burger and a different kind of drinks. Okay, so these are different combinations that we will talk about. So we can count it. This is the first kind of combination, the second kind, the third kind. So this is also discrete. So opposite to discrete will be something that is difficult to count, or there is no way to count. What things we cannot count? What things? What things? Yeah, so it's strange, right? There is really something that we cannot count, something that is continuous. Then this is very, very difficult to count. If you draw a line, okay, you draw a line, and then how many dots are inside this line? Then there are infinite number of points here. And later we will see that it is not just 1, 2, 3. We can never count the number of points on a line. Okay, so when we are using the radio or the television, so there are frequency that we're receiving. Okay, nowadays, so we may tune our television to a certain kind of a number, like 104 blah 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 dot kilohertz or whatever. Okay, so this may be something that we call it discrete. But then usually it is not just a single number. It is usually a range of real numbers that is in between. And in this case, these are things that is continuous. and this is difficult to count. So the good thing here is that we are not dealing with that. If things cannot be counted, it can create some problem. Okay? So we are going to talk about discrete math, and then why we are going to talk about discrete math in a computer science course. Why? So this is a computer science course, right? So why? So math is already strange. We're studying math in a computer science course, right? It's very, very strange. Why? Why? Okay, of course, there are history. Okay, computer science does not generate from nothing. It is generated, okay, or it is developed by a group of professors that has mathematical background. Even the first computer is designed by mathematicians, okay? So that's why you see that math is something that is related. But why we are talking about math in a computer science course? Okay, it is also because we are using a computer mainly to solve problems that we don't want to solve by ourselves. Okay? And in that case, you want the computer to solve a problem, what? Correctly, right? And then quickly. So these are some things that we need to keep in mind. But how do you know whether the computer is solving a problem correctly? In that case, we will need proofs. You need to prove that using a certain way, a certain kind of instructions, if the computer can follow these discrete instructions step by step, then it is going to solve the problem correctly, then it is what we want. So in here, we will need to prove this is correct and this is discrete thing. Proof is, okay, a discrete number of sentences that we have. And we also want to talk about whether a computer can solve a problem quickly, right? And then how do you measure how quick it is? So computer, we are running, I don't know how fast we are, 4 gigahertz or maybe more. Oh no. Oh, my old days, my machine, the fastest machine is 4 gigahertz. How is the speed of your computer? How fast? Do you know? 16 gigahertz or whatever? I don't know. I have no idea how fast a computer runs nowadays. Pardon? Maybe 4. Okay, let's say 4G. 4 gigahertz, what does it mean? It means that in 1 second, a computer can run 4 giga numbers of operations. Okay? So operations like you can add 2 numbers together. You can bring something from your RAM into the place that you can look at the numbers. Okay? So these are the operations that we are looking for. So to check how fast your computer can solve a problem, we need to count how many operations that we need to solve a problem, right? And that is discrete things. It is never continuous. Okay? Although the transistor inside may be relaying some kind of continuous idea to represent a 0 or 1 inside the computer, but in the end, when we are talking about how fast your program run, your computer can solve your problem, then it is the number of operations that we look at. And these are discrete things. So somehow, so this is a special branch of mathematics that is very related to computer science. Okay? So we will talk about things like this. Okay, so some very, I think it is some very interesting example I will show you, problems that we may consider in this course. So for instance, is there a way to find a consecutive, okay, so let me ask you first. Does anyone know what is prime? What is a prime number? A prime number? Anyone? Yes? Yeah? 指数. Okay, so a prime, yeah, very good. So a prime is a number, okay, usually we define it to be a number greater than 1. So you start counting from 2, okay. A number that has only 1 and itself as the divisor. So no other numbers can divide the number. No any other number can divide the number. So for instance, 7 is a prime because 7 has only 2 divisors, 1 and 7. Is that okay? But then 9 is not a prime. 9 is divisible apart from 1 and 9. It can be divided by 3 properly. Okay? Okay, so what are the primes? So 2 is a prime, 3 is a prime, right? And then the next one is 5, okay? And then the next one is 7, and then the next one is 11, 13, and so on and so forth, okay? So 2 and 3, in between the gap is 1. 3 and 5, in between the gap is 2. This is 2, and this is 4, and then this is 2. Is that okay? And then somehow the exact gap between consecutive primes is difficult to predict. And so far there is no way to, maybe this is what I guess, there is no way to predict what is the next prime. But on the opposite, if I ask you a question, is there some prime, let's say this is a prime, some prime, let's call it P. P is a prime. Let's say there is another prime, maybe this is the Q, such that in between there are no primes. But then the gap is very long. Let's say, can I have a gap of 1 million between 2 consecutive primes? What do you think? Would that be possible or would that be impossible? And let's get a vote. If you think it is impossible, could you please raise your hand? Okay, 1, 2. Okay, on the other hand, if you think it is possible, could you please raise your hand? Okay, good. Okay, good. Yes, it is possible. Okay, but then how do we show? How do we show? How do we show? Then here, this is something that is related to, you want to find a way of proving that this is correct. Okay, we will in this course we will introduce different kinds of proving techniques. And for this particular problem, let me tell you, there is one very beautiful proof. Okay, 1 million, right? Okay, 1 million. Okay, look at this number. So roughly, I will show you roughly the idea why it is working. So let's look at this number, 1 million. 1 million is a large number, right? Okay, 1 million plus 2 will be, a larger number. Okay. Now, let's look at the just 1 million will be enough. Okay, let's do the 1 million. So 1 million is a large number. And then let us take the factorial of this one. So what is 1 million factorial? So factorial is something like 5 factorial is 5 times 4 times 3 times 2 times 1. Okay, 10 factorial will be 10 times 9 times 8, blah, 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 up to 1. Okay, 1 million factorial, 1 million times 1 million minus, okay, you know. Okay, so it is a super, super large number. Okay, now, if I add 2 to it, this cannot be a prime. This cannot be a prime. Reason, it can be divisible by 2. Right? Okay, so let's look at another number, 1 million factorial plus 3. Yeah, this cannot be a prime because it can be divided by 3 properly. So we have 1 million, so you will see the trend. If I add 4 to it, it is still not a prime. So you have many, many numbers which are not prime. 1 million factorial plus 1 million. This is still not a prime. Okay? So what does it mean? So there may be a prime smaller than it. Okay, let's call it P. And there may be a prime greater than it. Let's call it Q. Then the gap between this P and Q will be very large. It has at least 1 million number, or roughly 1 million number here, at least. Okay, so that proves our claim. So our claim is that we are not finding P and Q such that exactly 1 million. Exactly 1 million may not be possible, but if it requires that the gap is greater than or equal to 1 million, then this is a proof. Okay? Now this is one kind of proving technique that we are going to talk about, and this is simple. The technique here is called what? Constructive proof. You construct a scenario that can help you prove what you want. Okay? There is a problem, a very basic problem in computer science called sorting. So I believe you haven't heard of this word before, right? So I don't know when I was in my undergraduate. So sorting is what? Okay, sorting is you have a lot of numbers, and then you want to arrange them from small to large. Then this is sorting. Okay, so why is it called sorting? I don't know. Maybe, okay, the usual way we call sorting is that you have you are using some playing cards like poker cards. Then I give you a hand, maybe you have got some number of cards like 13 cards, and then you want to rearrange the cards in some way that is convenient for your game. So this is kind of sorting. Sorting means that you put the card in some order, in some right order. So in computer science, the sorting problem is usually defined on you have a list of numbers, you have many numbers, and then you want to arrange them from small to large. Okay, so this is called a sorting problem. And then, okay, so let's say I have 3 numbers, A, B, C. Okay, so I have 3 numbers, A, B, C. And then we don't know what is the number behind it, but you can ask the computer to compare any 2 numbers at a time. So maybe you compare A and B. And then I will tell you which one is larger, which one is smaller. So you can pick A, B and compare. You can pick B, C and compare, whatever. So is there a way that we can use this kind of basic operation, compare, to find out from small to large? Yes, how? Yeah, how? Okay, compare 2 times? Maybe, yeah, let's see. So let's compare A and B. 3 times, okay, good. Let's see. Okay, so let's compare A and B, okay. Maybe A is greater than B. Okay, then what do we do? Okay, and then let's compare B and C. Maybe B is still greater than C. Okay, good. Then in this case, we know that A is greater than B is greater than C. Okay, but in a bad day, maybe this is smaller. Then what should we do? Then in that case, we compare A and C. Okay, so maybe this is greater. Then we know what? We know that A will be the greatest number because it is greater than any other 2 numbers. Is that okay? And then C is the middle one, and B is the smallest one. Okay, it works. Okay, so this is a method that we can sort 3 numbers. Okay, this method is by comparing every pair of numbers. Okay, so this is, we call it a method to solve something. Or, more commonly in computer science, we use a different word. Yes, very good. We use the word algorithm. Okay, yeah. Okay, algorithm. Okay, rhythm. Eh? Yeah, maybe this one. Okay, algorithm. Okay, is that okay? So algorithm means a well-defined sequence, or a well-defined sequence of steps that you can ask someone to do to solve a problem. Okay, if the sequence of steps can be carried out using paper or pencil, then this will also be perfect. So we're using paper and pen. Okay. Okay. So here we need to show that this. Okay, what we need to do? Okay, we need to show that why this algorithm works. Why? Okay, here we can show that. Okay, because after doing the comparison of 3 items, we must be able to find out one of them, which is the smallest. Okay, once the smallest is taken out, because we have the comparison between the remaining 2, we have a way to find out the second smallest. And so that we can then find out what is the largest. Okay, so this is a correct algorithm. And it takes how many steps? Maybe let's say comparison is the most time-consuming step. It takes time, okay, to do a comparison. But we know that there are 3 comparisons will be enough. Now but then we have an algorithm for just 3 numbers. Can we do something clever? So maybe this time I give you n numbers. N can be very large. Maybe let's say n is equal to 100. Then can we still solve a problem, a sorting problem with n numbers? Can we? Yes, how can? Yes, very good. Try more times. Okay, so actually, in one word, okay, make all the comparisons of all the numbers. Is that okay? If we can compare all the numbers, compare everything. Compare every 2 numbers. Then does it work? So compare every two numbers. We still do not show how we should do next. We have just the comparison. But then after we compare every two numbers, then what we can do? We can find out which number is the smallest one. If a number is being compared and then it is the smallest one each time, then it is the smallest one. In that case, I can find out the smallest number, and then the remaining 99 numbers, they are still compared pairwise. So we can repeat the argument to show that I can still find the next smallest number, and so on and so forth. So this works, right? Okay, but then to show that this is really working, what I have done, n is equal to 100, right? So I'm saying that, okay, I can take out the smallest number, and then I can use similar method to take out the next smallest number, and then I can use similar method to take out the next smallest number, and so on and so forth. So my proof is actually very long. I need to repeat some kind of arguments like this for 100 times or for 99 times. Is there something that we can do so that I can save some of my time to explain this concept? Okay, there is a powerful technique. I believe a lot of you have heard of it. There is a powerful technique called mathematical induction. Okay, have you heard of it? 数学归纳法. Okay. Okay, this is powerful. It is because I'm not going to repeat this argument for 100 times. What I'm showing is that I can, if a problem of size, let me see. I'm actually showing something like this. If a problem of size n-1 can be solved, then I can solve a problem of size n. Or put it in an easier way, so I'm saying something that is very clumsy. If I can sort n-1 numbers, then I can sort n numbers using this method of all comparison. If I can sort n-1 numbers, then I can sort n. The reason is that when I have n numbers, I can find out the smallest number. Then the problem suddenly becomes something that we know if I can solve n-1 numbers. So if I can solve n-1 numbers, then I'm going to ask the friend that helps me to solve n-1 number, the case. He solve it. And then together, including my observation of what is the smallest number, then we get a whole list of numbers that is arranging from small to large. Is that okay? So this is somehow, okay, we are going to talk about this properly when we have when we are developing the concept of proving. But this is the idea. So the technique of mathematical induction saves us a lot of effort. We don't need to repeat the same thing many times. We just need to prove, okay, one or two different arguments, and then we can show that it works for n is equal to 100. It also works for n is equal to 1 million. Is that okay? Okay, so this is about proofs that we have seen. This is to prove the correctness. And what else? Okay, so is it fast? Okay, if I have 100 numbers, then if I need to compare all of them, so how many comparisons do we need? How many? Okay, so this is a problem that is asked by a primary school teacher to Gauss. Okay. You should know Gauss, right? Okay, when he was, I forget, 11 years old or even younger, okay? So Gauss, so at that time, let me check. If you have heard about the story of Gauss adding numbers from 1 to 100, could you please raise your hand? Oh, that's very good. Okay, but anyone know who is, what kind of job that Gauss' father did? So Gauss is a mathematician, right? So Gauss has a father, right? Of course. And then, and then what is Gauss' father doing? Okay, Gauss' father is helping people to build a house. Okay, so when Gauss was very young, he usually looked at his father doing his job, counting the bricks. So old houses use brick to build, right? The red bricks, so count them. So somehow Gauss has some mathematical genius maybe come out from that time. So he's very, very sensitive to numbers. Okay, so Gauss method is, so you want to add 1 up to 100, so this is what Gauss is doing, right? You don't do this one time, you do this twice. And then he observed that if you do this, 2 times of your quantity will be equal to 101 plus 101 plus dot 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 up to 101 for 100 times. So the summation of all the numbers from 1 to 100 will be 10100 divided by 2. And it is going to be 5050, right? Okay, so here, if n is equal to 100 numbers, then roughly we are doing 5050 comparison, or a little bit less, 4950, okay, because we saved the last one, okay. But that's a lot. Okay, it grows. We call it the growing. It grows closely, not like n. It is closely like n squared, the square of n. Okay, now, a square of n, then what does it mean? That means that if you have a computer that runs with 4 gigahertz, okay, then you can solve a problem of n is equal to 100, of course, very quickly, because it just takes 5,000 operations, roughly. So it is very, very quick. So, but for a problem of size like this, is that okay? So if n is getting larger and larger, then let's say n is like this, then maybe you are needing something like 10 to the power 8 operations, roughly, okay, or in that order. And then maybe your computer can still solve it in less than 1 second. But now, if your problem size is 10 times larger, then it takes seconds. And then here, it takes hours. Is that minutes? Minutes or hours? 差不多, okay. Maybe this one, years or months, months or years. And then this maybe we will die already. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is going to be 10 to the power 16, right? But nowadays we have a lot of large records. So it is not actually a large number. It's not even, look at it. Eh? Median. This is median, right? Median. 10 million. 10 million. 1000万? Oh, 1000万. Okay, so this may be more than the total number of people in Taiwan. But still, it is not that large a number, right? So if you are using an algorithm that looks like this quadratic growth with a growth that close to n squared, then it may not be okay for some application. So we want to try to ask, okay, is there a better method? So in your, I believe you are going to study data structure soon. So in your programming course, advanced programming course, or the data structure course, you will learn some faster sorting technique. Okay, and then if you are lucky, then you can get an algorithm that runs in something like n times log of the n time. Okay, so log of the n is, usually we use a base 2 here. So what is log of the n? So what is the closest 2 power that exceeds n? So this is log of the n. So roughly speaking, so this is 10, this is 10, and this is something like 7. So in this example, this is roughly only 27 times 10 to the power how many? 8. Okay, something like this. Okay, so if you, so this is equal to what? So this is equal to, let's say 3, roughly. This is roughly like 3 times 10 to the power 9. Okay, 10 to the power 9 is giga. Okay, so roughly you take only seconds to solve a problem if you are running it in n log n time, if your method. On the other hand, if we are designing a bad method that runs in n squared, that grows like this, then yeah, we don't get the answer before, most probably before our life ends. Okay, so this is another thing that we are going to focus later, when you study the computer science course, we need to know why an algorithm is correct and how fast your algorithm is. And then you can know, is there any way to make your algorithm faster and faster?